Good morning, ladies and gentlemen. Thank you for your friendly invitation. What I want to show you from our surveying practice is a new concept for geodetic monitoring based on fiber optic sensing. I want to introduce you our group, which is settled in the northern, I'm sorry for that, but it's settled in the northern part of Austria. We have two base offices for our surveying company, one in Zwettl and one in Weidhofen. And we have our fiber optic team, exists also of another companies, which is Fibreoptic company, our development and research part in Prague, and also our NBG holding group, which is settled in Gmünd. Normally, what has fiberglass cables, what have they to do with surveying? Normally, we avoid to bend, to strain, to use tension or pressure on a LVL cable. So we hide it, we protect it. And for the surveying, sensing use of FOS systems, we look for that bending, straining, the influence of tension and pressure on the cable. So we make that distortions, that circumstances measurable. Our group is working on fiber optic since 5 years, and we started to make the first application of fiber optic 5 years ago in our area with a bridge, a railway bridge, to use all these FOS techniques. In the current status of FOS, it's a part of, let's say, technical standard on the universities, but it's not part of the technical standard in the daily practice. You have three main types of measuring with a fiber optic cable. You have, first of all, the point sensors, FBG, then the semi-distributed sensoring or the distributed sensoring. First, the FBG sensoring means that, for example, you have a point measurement for a crack or a point measurement for a movement of a rail. The semi-distributed sensoring means that you use the cable as a sensor on special spots and points on the cable. And the third thing, the distributed sensoring, is to use a cable as a sensor. This is, in very easy terms, describe the different types of fiber optic sensoring, and we will show you that it's not a theoretical application, but it's also well used in our daily practice, and that at the end of the presentation we will give you the state-of-the-art development we made in the last years. You see a different type and a various type of sensor applications which can be filled with different measurement techniques. A wide area for FBG sensors, from bridge monitoring to structural health monitoring, and also wide, bright field for the distributed acoustic sensing, from pipeline monitoring up to the direct heatings, to the fire monitoring, to the dam and landslide monitoring. We will go on that in detail in my practical examples and later on. The real advantage of fiber optic sensoring is that you don't have to discrete points in advance, and that you also not only have you can go in the object. So, for example, you can give the fibers in the concrete. For example, with the new tunneling methods, we put the LVL sensors in the concrete when they are erected. You have also no more sensor infrastructure on site. As you see that in the example, you can also use existing LVL installation. You have no more hardly support efforts of sensor technology if you compare it to robot tachyometer systems on site. It's really safe and hardly apprehended infrastructure. And finally, for our customers like railways or highway owners, if you install it once, you don't have to enter the infrastructure railway anytime more. To give an overview about the principle, you have this graphic. You have here the objects you want to monitoring. You have different group of sensors, and then you can connect up to 25 sensors with a standard cable up to 20 kilometers in an operating center. This means a measurement unit which needs power, internet, and all the other things is in a housing which can be 20 kilometers far away. We use only existing fiber optic links via LVL cable. Some projects we already realized and which are also successfully, mostly successfully fulfilled. A big bridge in our area. We did monitoring for the 2 old tunnels on the way from Salzburg to Vienna to the period of 2012 to 2014 until the new version of this railway went in daily work. Some bridges in Scherding. We monitored the huge Bosruk tunnel through the Alps. We did a famous crack detection and the Pacha tunnel, which is beneath the European bridge on Brenner. We did some acoustic monitoring in Gesäuse, and we also erected a test center in our area, and we did some projects in Czechia. And finally, we want to introduce you the Object Sense system. First project was a classical bridge movement in our area. You see a new road under a railway, and it started to crack. You see on the right picture below, and we did install a monitoring system with vertical, horizontal strain sensors, and which are permanently 24 hours, 7 days a week under measurement. So we put 18. Sorry for that, there is some installation here to go automatically and I can't stop it, but I try my best. There is an installation with 18 sensors on this bridge in all directions, also of course with temperature sensors, and with 2 additional vertical sensors for monitor the tracks of trains. You have, for example, one result of that strain sensor. You see the path of a train. You see the first signal. The level signal starts in the phase 1. Then you have the path of the 2 locomotives. Then you have phase 2, where you have empty wagons. Then the phase 3 is heavily loaded timber wagons. And then after you have a lot of empty wagons, and finally the signal goes back to the start. So our experts from the railway companies, for example, use that information, for example, to count the axis. And they use it even for detect errors on the axis behavior. And this is for the future of time life and life cycles of railways a very important thing. The mentioned project in Tunnel Reckawinkel and Düriberg was a detection of the surrounding of the tunnel. We installed 22 points, like a membrane, and the error level was set to 1 millimeter, and it's automatically system working since 2012. And the operator on duty get an information if one of the 22 strain sensors reaches this 1 millimeter level, and you see on the right side down, you see a short time period, and you see the black line is temperature, and you see the green line, which is the movement of this membrane. Another huge project was a temporary bridge in Scherding. It's a main line between Wels and Passau. So you have four lines for the daily business, and you have dozens of trains at 1 hour. And we installed there our band line system since about 6 months. And the results, band lines, just to explain, is a line of 5 meter. Sorry for that. Is a line of 5 meter with FPG sensors up and down, and through the horizontal movement, we calculate the vertical extension of the bridge, the temporary bridge, and also there we installed an alarm system 24 hours a day for our partners of ÖBB. I give you, if you look at one thing which is very, very new with our technique. What is the difference to our standard techniques? If you look at a train, at the typical behavior of a train with a bad construction surface. There you have some airbags which moves under the full weight of the train, but normally we geodetical way, we just can put it, we can measure it just when the train was passed. With fiber optic systems, we can not only measure the permanent data of the bridge, but also we can measure it, and I show you after, we can measure it when the train goes by. This is a standard typical picture. You have here the bridge, you have the direction of shedding, the direction of wells, and this is a 10-meter level. These are the bridge start and the bridge end, and you see the movement of the bend lines. And the most dangerous thing is if the red lines in one iron is here and on the other is on the different side. So because you have a big problem between the two irons for a train, and this is a mostly dangerous thing. But as I mentioned, the difference to other techniques is we also can measure with fiber optic the movement of the bend lines and the irons through the passing of the train. If you look at the signal, the standard signal for before and after the train passes, then you have the train passing. You see the amplitude with the full weight and the amplitude from unloaded double axis. And if the amplitude of the passing train changes significantly, you can be sure that there is a change in the surface of the railway. And this is a new technique which is very famous for the ÖBB infrastructure company, because they like this information even more than the standard technical and geodetical measurements. Our next project was the bottom phase in the Bosruk tunnel we installed during the last renovation phase in November 2013. We installed grids and fiber optic cables in the surface to get the movement of the rocks, and we also installed FPG's cover sensors for the installation. It's on the back here to get the movement and the vibration of these concrete coverages. The thing is installed since November 2013 and gives us at some spaces an idea of the movement. We have in that scale, we have a movement about the period 10-13 in the first 6 weeks, a movement about 1.2 millimeters. It's micrometer, so it's 1.2 millimeters, and the channel now is on these spots, it's stable, so we can prove that there is no abnormal situation and abnormal movement. Additionally, a crack detection project in Pacha tunnel, a very famous tunnel below the European bridge and Brenner. We have 12 cracks in this tunnel which are mounted, which are monitored by FPG technique. So you see one mountain here, one big crack at the beginning of the tunnel, and here we have a FPG sensor which is installed permanently, and we get the measurement data from this crack. We're talking about, I'm sorry that it makes me running. We are talking about 0.5, 0 to 0.1 millimeter in the short time and in the long time period. So the alarming situation, the limit is 1 millimeter. We didn't exceed this in the last 1.5 years. Another example of the Pacha tunnel. One very interesting part is for the LVL structure is to use the LVL infrastructure of a partner. So for example, for the Austrian infrastructure company, they have on the main lines, they have LVL information already existing, and they have reserves to use for other things. So we started a research project for use of fiber optic sensors in the field of the ÖBB infrastructure, together with the University of Graz and other partners, and an accreditation for long-term installation with the German BAM, just to use the LVL system for LVL monitoring and FBG monitoring, and we are in the finishing of this research project. It's very promising, and it should change significantly some applications within the ÖBB infrastructure. One of that projects, it's an amazing thing in Gesäuse, where we use distributed acoustic monitoring. It's about detection of rocks on the irons. There is an existing LVL cable in this 35 kilometer stretch, and we use just the cable as a sensor, and our project is to detect stones from the height and from the weight, and the short result on that is this picture. You see on this picture the signal, the behavior of this distributed sensor. You have here the distance in meters, up to 6 kilometers, and here the time. And what you see on this acoustic, as the name say, acoustic sounding, what you see is, for example, some working on the irons. Here you see a train passing, and finally, in a distance of 5.2 kilometers, you see two rocks, which was detected by these fiber optic measurement techniques. You can compare that to a microphone via LVL cable, and we use it, for example, for that application. And for that reason, we also erected a field laboratory in the area up to my office in Zwettl. It's an old railway stretch. We bought this 300 meters. We installed a new LVL cable infrastructure, and installed there a small test center with an own LVL cable. And we have international guests here from Iran up to Russia to use that test center for rock detection and also for other things in the railway field. Finally, I come to the end with our latest baby. We call it Object Sense. It's a very easy and old geodetic idea. Permanent digital leveling without any infrastructure on the site. So we developed this Object Sense, which is simply the same like we in our geodetic world know up today. A prism on the rail and an information device and sensoring device on a stable construction. So far so good. What's the difference? The difference is very easy. Our measurement device, which you can see here, is installed, as I mentioned, permanently. You see the prisms on the irons, but the measurement unit can be 20 kilometers away from the site. So no power, no brain on site. And you see here the latest installation in Lietzen in the south. And the measurement station, the instrument could be 20 kilometers away in the railway station. So I need nothing more than, we don't need more than the Object Sense on the site. You see here the bridge construction. We have 4 of these prisms installed on the railways, and this installation is permanently running. If you like, you could look at the measurement data there on our booth. This is a system in graphical detail. You have the 4 optical heads, 4 prisms on the irons on the railways, and the interrogation unit housing, which is in this way, in this application, very close, but it can be up to 20 kilometers away. And if you look at the measurement data, these are the 4 sensors. The 4 sensors at Lietzen 2. You have a scale in millimeters here. You see the results on all the 4 sensors. Every of these markers is a train passing, and the other sensors on the other side. And at the moment the data are satisfied, so we have no anomal settlement of the railways, and the trains can pass this constructing area. Keep in mind that it's an instrument where we have our intelligent up to 20 kilometers away, and where we can use existing LVL infrastructure. So if we have highway or you have railway infrastructure, you can use that just to splice on that, and you use the LVL cables to supply that system, which is, I think, some revolution in our geodetical world, and where we already started to install that on different spots, and we're sure that it will be a very new technique in our geodetic world, and in the next INTERGEOs, let's say 15, now 16, 17, you will see several booths where you have FOS as a standard technique installed. Ladies and gentlemen, thank you for your attention. Glück auf and have a nice day on the INTERGEO.